Okay, welcome Chem 652 students. Since there was a partial snow day today, we didn't have our review session. So we're going to review now for the final exam. And it's always difficult to do this by video since I don't know what your questions are. So what I thought I would do is I would let you know that it's going to be a really hard final exam. And probably you feel like you've been inundated with a lot of reactions lately in the last couple of chapters. So I thought what I would do today is review all those reactions. It's hard to review everything for the semester. This would be about a 5-hour video. I want to keep it fairly short. So I'm going to focus on the last couple of chapters and all the new reactions you've learned. Most of these reactions, pretty much all of them, have involved either alkenes or alkynes. We're going to start with the alkenes. So here we go. You might remember that it is possible to cyclopropionate an alkene to add a cyclopropyl group right where the pi bond used to be using diazomethane, CH2N2, and either heat or light, although light is preferred. So when we do that, we add the cyclopropyl group. It's only one atom that forms that new three-membered ring, the carbon atom of the methylene group right there. And so it has to be a syn addition, no doubt about it. You can show it either in front or in back. It approaches either from the front face or the back face. It doesn't matter. This is not a chiral compound. There's a plane of symmetry. So those are exactly the same. It is also possible to form a three-membered ring using a per acid like MCPBA. And when we do that, we have a three-membered ring in which the new atom in that three-membered ring is an oxygen. We've talked about the fact that this epoxide or oxirane is pretty special because it's quite reactive, yet at the same time it's isolable and very manageable to work with. One of the reactions it undergoes is hydrolysis. If we hydrolyze this, we can produce the corresponding anti-vicinal diol, which would be produced as a racemic mixture. And we have two different ways to hydrolyze it. We can either do that in aqueous acidic conditions, H3O, H2O plus, H3O plus H2O, or OH minus H2O. Both of those lead to the anti-vicinal diol product. It is also possible to take this oxirane and react it in other ways. We've talked about the fact that since it's so reactive, strong nucleophiles will ring open the three-membered ring. And so, for example, we could use a Grignard reagent or an organolithium. It doesn't really matter what the organic component is. It would be something. It would either be a methyl, ethyl, propyl, phenyl, what have you. It would be something, but we'll be generic about it here, and we'll just say RMGX, where X is either chlorine or bromine in the first step, and in the second step, H2O, H3O plus to quench the alkoxide that's formed. And remember, we don't have to use a Grignard reagent, so actually we could use the corresponding organolithium here as well. In both those cases, we're going to ring open the epoxide, to form an alcohol. Now if you look at these two reactions, they're very similar. Here we hydrolyze the epoxide, and the nucleophile in the hydrolysis is either hydroxide if we run this under basic aqueous conditions, or H2O if we run it under acidic conditions, and as a result we add an OH group in addition to the oxygen that was already present. Here our nucleophile is this carbon containing R group here. There our nucleophile came in, ring open the epoxide, and eventually we get the OH in the same spot. So these reactions have a lot in common mechanistically and structurally. Well, as long as we've shown that it's possible to make this anti-vicinal diol through hydrolysis of an epoxide, let's go ahead and talk about how to make a syn-vicinal diol. We know a couple of different ways to do that. Potassium permanganate under aqueous basic conditions we'll take our alkene to the corresponding syn vicinal diol. In fact, we can get there another way. If we use osmium tetroxide in the first step, followed by a reduction, we can get to the same syn vicinal diol. So these reactions over in this side of the page have a lot in common, in some cases both structurally and mechanistically, and in all cases structurally. But they're not identical, of course, so back up here to the hydrolysis of the epoxide, let's make sure we note that this is an anti-vicinal diol, whereas the syn vicinal diol is made in one of these two fashions. Alright, let's go on to some other reactions. How about if we just try a Markovnikov hydration? Now in this particular case, our alkene is evenly substituted. Both carbons of the alkene are secondary. So although we're going to perform a Markovnikov hydration, it doesn't really matter which carbon gets the hydrogen and which carbon gets the OH. They're both secondary. How can we do this? We can either do this the old-fashioned way, an acid-catalyzed hydrolysis, notice that when we add hydrogen across one of those carbons and OH across the other, we make cyclohexanol, which is not chiral. There's not a syn or an anti-addition associated with this. This is a reaction that involves a carbocation, so there's no particular stereochemistry. And likewise, we can get to the same product in a two-step sequence called oxymercuration, where in the first step we would add mercuric acetate in aqueous solution, and in the second step a reduction using sodium borohydride to give us the same Markovnikov product, Markovnikov hydration product. What else do we have? Well, you might remember that we can hydrohalogenate, that is add HX, where X is either chlorine or bromine or iodine. And in this case, again, it's going to be a Markovnikov process, but we've got two equally substituted carbons of that alkene, so it doesn't really matter which carbon you put the hydrogen on and which carbon you put the X on. And just as in the previous case, we're not going to make a chiral product. We've got a cyclohexyl halide. Okay? In addition to hydrohalogenation, we can halogenate. So for example, if I add X2 in an organic solvent, you don't necessarily have to indicate the solvent in this reaction, but I'm going to choose a typical organic solvent, which might be methylene chloride. Here, X is going to be either chlorine or bromine, not iodine. The reaction with iodine is sluggish. And what's interesting is that you make here the anti-vicinal dihalide. Now there are some derivatives or relatives of this reaction which are very similar, but they give rise to slightly different structures. The first is halohydrin formation. So if I try to run the exact same reaction, except that I switch up my solvent from one that is inert or unreactive, like methylene chloride, to one that is nucleophilic, like water, that water will trap the intermediate halonium ion, and instead of forming this anti-vicinal diol, I will form a halohydrin. Still anti, just like the addition of the halide was. And it should be, because both of these reactions start exactly the same way, with formation of a halonium ion intermediate, which is then attacked by nucleophile. In the organic solvent, the nucleophile is going to be the X-, the second half of that X2 compound that added in to form the halonium ion. In water, that X- is likely to dissociate away because water is polar, leaving the weak nucleophile water, which then attacks on the opposite side of the halonium ion to give us this halohydrin. Now in both of these cases, these are chiral products, so we need to indicate that we would form a racemic mixture. Okay, let's keep going. Very closely related to both of those is so-called halo ether formation, where instead of using water as my solvent, I'm just going to use an alcohol. Instead of HOH, I'm using ROH. And once again, I'm going to produce an anti-product as a racemic mixture. This one is called a halo ether. So all of those are very closely related for sure. What else do we have? Well, I've left off a reaction called ozonolysis, which is very important, so we're going to talk about ozonolysis next. Here we go. If I take this alkene and I try an ozonolysis reaction, you might remember that this ozonolysis reaction involves ozone, O3, in the first step. And we talked about the fact that the ozonolysis reaction is just going to simply break that carbon-carbon double bond in half. And where there were carbon-carbon double bonds, they'll now be carbon-oxygen double bonds. And so if I do that on this cyclic compound, let's see what that would look like. Since I'm breaking this carbon-carbon double bond right here, I'm going to elongate the pieces apart from each other. And I'm going to substitute in carbon-oxygen double bonds where there used to be carbon-carbon double bonds. And it looks kind of funny because I'm drawing this molecule in a conformation where these two carbon-oxygen double bonds are right on top of one another. But what I want you to note, going back to this alkene, is that there are a couple of hydrogens here at the alkene site, and those hydrogens would now be here and here. Maybe. It depends upon whether we do an oxidative or a reductive workup. What I hope you remember is that if we do an oxidative workup, which would be hydrogen peroxide, then we oxidize the aldehydes that are formed. If this is a hydrogen, this is an aldehyde group. We oxidize aldehydes all the way to carboxylic acids. This one would also be an aldehyde, so it would be oxidized to the corresponding carboxylic acid. Now what's unique about this reaction compared to the ones we did in class recently is we started with a ring compound, so when you chop that alkene in half, we still have one molecule. The carboxylic acid piece here is not located on a separate molecule relative to this carboxylic acid. They're tied together by the ring. We should have 6 carbons, 1, 2, 3, 4, 5, 6, because we started with 1, 2, 3, 4, 5, 6. We still have 6 carbons. Probably a more typical way to draw this molecule right here, so I'll write OR, drawn this way, 1, 2, 3, 4, 5, 6, would be to draw it out in that fashion. But those are the same molecule, and if you draw it this way, that's perfectly fine. Well, last thing about ozonolysis is that if we run this ozonolysis reaction under reductive workup conditions, we do not over-oxidize to the carboxylic acid. We can maintain the aldehydes that might form. So in this case, we'll start off with ozone in the first step, and in the second step we need reductive workup conditions. You've actually got 3 sets of reductive workup conditions. The first is hydrogen with palladium, or you can use dimethyl sulfide, or you can use zinc H2O. That would be zinc dust, zinc metal H2O. You don't need all 3 of those, you just need to pick one of them. And when you do that, let's see if I can squeeze this in here. You get the corresponding aldehyde. Notice that the hydrogen that was present initially here and here is still present. It hasn't been over-oxidized to the carboxylic acid like we saw under oxidative workup conditions. And what we could say is that this is more typically going to be drawn in the following way. 1, 2, 3, 4, 5, 6. As the dialdehyde. So that's a lot of reactions. all from alkenes. I think that's most, if not all, of the alkene reactions we've studied in the last couple of weeks. A couple of those reactions were Markovnikov in nature, and so I'd like to actually go back and repeat myself now and just show maybe 3 or 4 reactions on a slightly different alkene. So I'm going to choose still a cyclic ring, a 6-membered ring here, but one in which one of the carbons is less substituted. That's secondary because it's attached to 2 other carbons, and the other carbon of the alkene is tertiary because it's attached to 3 other carbons. So let's talk about the reactions that were Markovnikov. Well, one of them is hydrohalogenation. So we're adding HCl or HBr or HI. And in this case, because it's Markovnikov, our modern translation of Markovnikov's rule is that the reaction proceeds in such a way as to form the most stable carbocation, which frequently means that the hydrogen will go to the less substituted carbon and the halide goes to the more substituted carbon. And that's exactly what would happen here. Notice that it is okay to draw these bonds as lines here. This is not a stereogenic center, so you don't have to indicate the 3-dimensional nature of this, but it would also be okay to go ahead and indicate the 3-dimensional nature. In that case, you're going to put one of these groups, in this case I've arbitrarily chosen the methyl in front and the X group in the back. If you took that molecule and turned it over, you'd now have the X in the front and the methyl in the back. It doesn't make a bit of difference which one you show where, because again, this is not a stereogenic center. So that is our Markovnikov hydrohalogenation. Protonation would occur at the less substituted carbon to give the more highly substituted, more stable carbocation intermediate, and that's where the nucleophile adds. All right, let's try hydration. Good old-fashioned acid-catalyzed hydration would give you the same sort of a result. In this case, we're adding hydrogen across the less substituted and OH across the more substituted to give us the alcohol. Again, you can show it like this, or you could show it like this, where instead of X you've got an OH. It's all good. We know that you can also get there in an oxymercuration reduction sequence as well. Now, this oxymercuration reduction does not involve carbocations. It involves a mercurinium ion, which is a 3-centered 2-electron bond. It's different than a carbocation. So there's no possibility for a carbocation rearrangement. But as it turns out, there was no possibility for a carbocation rearrangement here anyway, because on Markovnikov protonation of the alkene, we generate the tertiary carbocation. That's not going to rearrange to anything less stable, so both of these reactions lead to exactly the same product. I think one of the reactions that I left off the page in the previous set of reactions I showed you was this one right here. This is a hydroboration oxidation sequence, and this occurs in an anti-Markovnikov fashion. An anti-Markovnikov fashion means that instead of adding the hydrogen to the less substituted carbon, we're actually going to add it to the more, and the OH winds up on the less. So it's exactly the opposite of Markovnikov, hence anti-Markovnikov. We're not breaking Markovnikov's rule when we run this reaction because the reaction does not involve carbocations. It's anti-Markovnikov because of the way in which the borane cycloadds across that pi bond in the first step. It's also a syn addition. That's a net syn addition, and so we need to indicate that. So for example, if I show the hydrogen adding here and the OH adding here, which is what I need to do for an anti-Markovnikov fashion, and I show them adding from the top face, then my oops, look at that. I'm doing a Markovnikov reaction. Sorry. If I show the hydrogen adding here and the OH adding here, I don't know if that's what I just said a moment ago, but that's what I need for an anti-Markovnikov hydration. Then in that case, I would get a structure that looks like this. So here's my anti-Markovnikov hydration. Hydrogen's added across the more, substituted OH across the less. This is a chiral compound, so it must form as a racemic mixture. And all that really means is that instead of adding across the top face, I could just as easily have added across the bottom face to form the enantiomer. Okay, so here we've covered Markovnikov reactions. These are all Markovnikov. And an anti-Markovnikov reaction. Okay, very good. One more thing I want to cover with alkenes before we move on to alkynes, and that is those cases where it is possible to have a rearrangement, a Wagner-Meerwein rearrangement. So, for example, if we were to run a simple hydrohalogenation reaction on this molecule, we would expect that we would add the hydrogen, that is protonate, across the less substituted carbon to form the more highly substituted secondary carbocation, and perhaps form a product that looks like this. But that will only be the minor product. The major product will actually look like that. So how did that happen? This is an example of a reaction that involves a Wagner-Meerwein rearrangement. If we look at it mechanistically, we begin with protonation of the pi bond to give us a secondary carbocation, but it turns out with a simple methide transfer, we can move a methyl group and the 2 electrons of that carbon-carbon bond over to this position to give us a tertiary carbocation. And this is when we see these Wagner-Meerwein rearrangements, whenever it's possible to convert a secondary carbocation to a tertiary. There's no incentive to move one secondary to another secondary, or to move a secondary to a primary. Primary carbocations are never going to form in solution. There's no incentive to move a tertiary to a secondary, etc., etc. The only thing we're going to see, the only times we're going to see a Wagner-Meerwein rearrangement is when we go from a less stable carbocation to a more stable carbocation. Now at the same moment that we've protonated, we've also produced the X minus anion with this second arrow, 2 electron arrow, which was missing until a moment ago. We see from that arrow formalism that the halide anion is formed. It is conceivable that the halide anion would trap the secondary carbocation through path A, but this Wagner-Meerwein rearrangement is going to be quite rapid, and that's not going to be competitive with path B. Or in other words, saying that is that the Wagner-Meerwein rearrangement is faster, generally speaking, than nucleophilic addition to the carbocation, and that's why path B leads to the major product, whereas path A leads to the minor product. Well, as long as we're talking the possibility of carbocation rearrangements, let's finish this discussion with the oxymercuration reduction sequence. As we saw on the previous page, this is an example of a procedure that gives rise to a Markovnikov hydration, but it does so without the possibility for a carbocation rearrangement because carbocations are not involved. So in this case, we're not going to form this secondary carbocation. We form that mercurinium ion that we've discussed before, which is not a carbocation, and it does not undergo a carbocation rearrangement, the only thing we form is this alcohol through addition of H and OH, H and OH in a Markovnikov fashion without the possibility for carbocation rearrangement. So that's our major product and our only product. Alright, that's quite a bit on alkenes. I'd like to show you one reaction which you learned a while ago, several chapters ago. This is not such a recent one, but it's closely related to these. It came in the chapter where we discussed the consequences of conjugation. It's a reaction of a diene with, let's say, HX. And what we saw there is that we actually can form two different products, and really three if we consider the fact that that last product can form as either the E or Z isomer. Okay, how does this happen? Again, this is a reaction that falls under the category of consequences of conjugation, and it ties in resonance, which we learned at the beginning of the semester, and it's kind of popped back up at different periods of time. It's going to continue to pop back up in a big way in the near future as we enter organic chemistry too. We know that this hydrohalogenation is a Markovnikov process, which means again that it is a process that is going to involve formation of the most stable carbocation. Well, if you look at the diene, we've got two carbons, this one and this one, which I've just placed in boxes, which are both primary, and these two, which are both secondary. So it would seem logical that protonation should occur at the less substituted carbon to form the more highly substituted carbocation, and it doesn't really matter whether you show protonation there or there, you're going to form a secondary carbocation either way, and they're identical to each other. It turns out that will be the correct path. Let me redraw this without the boxes and triangles. That will be the correct path, but the reason it's the correct path is not necessarily obvious until we draw it. So if I protonate at this carbon here, the less substituted carbon of this alkene, to form the secondary carbocation, this pi bond is still in place. I didn't touch that one. That is not really a secondary carbocation, as it turns out. It is rather a resonance delocalized carbocation. So you might remember we talked about the hot potato theory. If we can delocalize that positive charge over a larger volume, in this case over two carbon atoms, that's always going to be much better than having the positive charge centralized or located just at one carbon, whether it's primary, secondary, or tertiary. Resonance delocalized carbocations are the best. So by protonating at the less substituted carbon, we didn't form a secondary carbocation, we formed a resonance delocalized carbocation, which is absolutely the best carbocation we could form in this case. And it's important to remember that these are resonance forms, so these are not two distinct molecules or two different molecules, they are just one molecule. We need two resonance forms to describe this one molecule, which means that the charge is not located at that carbon some of the time and at that carbon some of the time. The charge is located at both carbons all of the time. They both have positive charge character. The second half of this arrow formalism is the formation of the halide anion, which is going to be our nucleophile. Because the positive charge is located at both carbons, the halide is going to attack both carbons. And we would expect to produce two different products. And there they are, as a result of the positive charge, as a result of the nucleophile attacking the two carbons which are electrophilic, the two with the positive charge in those two resonance forms. Now, had I shown this particular carbocation in a conformation in which this methyl group was down, then I would have produced a resonance form in which I had, rather than a trans-looking alkene here, a cis-looking alkene. And so, as is customary, whenever you can produce a trans or E alkene as a product, you're probably also going to be producing the corresponding cis, so that's also one of our products. So this reaction falls under the category effects of conjugation, and it involves resonance. If we were drawing this mechanism out, it would be okay to show this nucleophile attacking both sites. Nice to label it as either A or B or 1 or 2. And then go ahead, since this is the product of path A, to call that A, and this is the product of path B, to call that B. Very good. Okay. Now let's just wrap this up by talking a little bit about alkynes. And so what I want you to remember is that alkyne chemistry and alkene chemistry are very closely related to one another. Not surprising at all, since all of these reactions involve cleavage of the pi bond. The alkene has 1 pi bond, the alkyne has 2. So, for example, if I were to take this alkyne, and I've chosen one that is terminal, notice that the molecule terminates right here with the alkyne function. There's a hydrogen at this end, whereas this R group implies there's something organic over here, and it could be very large or it could be as small as a methyl group. But it's a terminal alkyne nonetheless. A couple of reactions we've learned. One is that we can hit this alkyne with excess X2. And what we're going to do is we're going to halogenate twice. So we're going to add XX across the first pi bond and then XX across the second pi bond. And the result will be that we will produce a molecule that looks like this. This is a tetra halide. And it is important for forming the tetrahalide to use an excess of the X2, because in principle, if we'd only added 1 equivalent of X2, the reaction could stop after 1 addition. It's not a great idea to try to produce that product in which we've only added 1 X2 equivalent, because it's going to be a messy reaction mixture, a messy product mixture, I should say. It's all but impossible to form that product in which we've added just 1 equivalent of X2 in high yield. That alkene dihalide will, at least in part, continue to halogenate all the way to the tetrahalide. So at the end of the day, we'd have a mixture of our starting material, which is unreacted, plus the alkene dihalide, plus the tetrahalide. It's cleaner just to use an excess of X2 and to drive this all the way to the tetrahalide in high yield. So that's the way we've talked about it in class, and that's the way we run that reaction. Likewise, if we just hydrohalogenate, we're going to use an excess of HX. So in this case, we're going to protonate at the less substituted carbon in Markovnikov fashion, add X at the more substituted carbon. We'll do that once, there'll still be 1 pi bond left, and then we'll do it a second time. And the result is that we form this geminal dihalide. Notice that by protonating twice at that less substituted carbon, not at the same time of course, but over the course of the entire reaction we protonate twice, we generate a methyl group. Okay, what else? Well, we learned that we can hydrate alkynes in a couple of different ways. We can do it in a Markovnikov or an anti-Markovnikov fashion. Let's start with Markovnikov hydration. For this reaction, we use mercuric acetate again, this time just in aqueous acidic reaction conditions. Not necessary to use a two-step sequence as we did with alkenes. And although it's not necessary, I've told you in class that it's actually quite useful for you to draw the enol structure first that forms. So if we're following along and we recognize that this is a Markovnikov hydration, we're going to add hydrogen and OH across the carbons in this fashion, hydrogen and OH. Our R group is still there and the starting hydrogen is still here. This is an enol, an alkene and an alcohol all in one, and it is going to equilibrate to the corresponding carbonyl, where this pi bond essentially moves between carbon-carbon to carbon-oxygen, and the hydrogen essentially moves over to this alpha position over here, and the result is that we get a ketone. This is a ketone because there are two R groups. It's a methyl group here. We don't know what that R is here. It could be just about anything. And a carbonyl group in the middle of those two R groups, and that's a ketone function. If we ran an anti-Markovnikov hydration, and we're going to run that in pretty much the same way we run an anti-Markovnikov hydration of an alkene, except that instead of using borane, BH3, we're going to use a bulky borane, an organoborane. The reason we want to do that is we don't want to hydroborate both of those pi bonds. And if we used borane, after we added borane across the first pi bond, we would have an organoborane in which there's still two boron hydrides, which could in fact continue to react, and the reaction might get a little messy. So instead, we use a borane in which there's only one bond to hydrogen. It's bulky, so it will slow down any sort of oligomerization reactions where we're just let this thing run on and on and on. The second step is going to look the same, and so we're going to effectively run here an anti-Markovnikov hydration of this alkyne. Once again, I think it's wise for you to recognize that you're reacting one of the pi bonds. So notice there's no triple bond here anymore. It's an alkene now. And I've got the right bond angles drawn in here. You're hydrating in an anti-Markovnikov fashion, which means hydrogen is adding across the more substituted and OH across the less substituted. Once again, that gives rise to an enol, just as we had over here. But in this case, when that enol equilibrates to the corresponding carbonyl, our carbon-oxygen double bond will be right there. All that's left over here is a hydrogen. This hydrogen effectively or essentially moves over to this carbon, and we produce an aldehyde. So you can produce either ketones or aldehydes depending upon how you hydrate a terminal alkyne. If this were an internal alkyne, it wouldn't really matter whether we use Markovnikov or anti-Markovnikov conditions. You'd only form ketones. But by choosing a terminal alkyne with an anti-Markovnikov hydration, we can actually produce the corresponding aldehyde. The details of these equilibria process between the enols and the ketones, or the enols and the aldehydes, will be presented in Organic Chemistry 2 when we study aldehydes and ketones. You'll see these reactions again. Right now, I'm not worried that you know the mechanism for that conversion from enol to aldehyde. I just want you to recognize how to show formation of the corresponding aldehyde or ketone structures starting with their corresponding enols. All right, we're down to our last set of reactions. Let's go to an alkyne that is internal. So here is an internal alkyne, and what I want to show you are the three different hydrogenation reactions which are possible. If we just use regular old alkene hydrogenation conditions, which means hydrogen in the presence of a transition metal catalyst like platinum or palladium, then we are simply going to hydrogenate twice. We're going to hydrogenate both pi bonds, and we're going to wind up with the corresponding alkane. So instead of having a carbon-carbon triple bond here, both of these are methylenes because I've added hydrogen across the first pi bond and then across the second pi bond. That forms the corresponding alkane. If we would like to stop the reaction at the alkene stage, we need to use a poisoned catalyst, Lindlar's catalyst. In this case, hydrogenation will occur in a syn fashion, and you can stop the reaction at that Z alkene. On the other hand, if you'd prefer to make the E alkene, you can do that as well using a dissolving metal reduction reaction, sodium in liquid ammonia, and that will produce the corresponding trans or E alkene. So those are our 3 hydrogenation reactions involving alkyne, and with those 3 I think we've covered all the major alkyne reactions that we've studied. We've already covered all the major alkene reactions. That's most, if not all, of the reactions you've seen in the last couple of chapters, and even 1 or 2 that date back further than that. I hope that was a good review for you. I will see you at the final exam. Good luck.